So this is the 2008 Scholarship Physics paper, NZQA, NCEA, whatever, and it's question 1 to do with spectroscopy. When viewing white light from a glowing source through a spectroscope, and a spectroscope is something which just separates out the colours in the spectrum from that light that's going into it. So when viewing white light from a glowing source through a spectroscope is seen. If a gas is now placed between the source and the spectroscope, the spectrum shows dark absorption lines. Explain fully how these lines are formed. So when we just sketch this out, we've got white light coming in, and we've now got a gas cloud. Okay, and that light is passing through and then coming out essentially to the spectroscope is going to show a spectrum, so I'm just going to draw that as a screen. Okay, and we should see, you can think of the spectroscope as a prism separating out all the bits, so we're going to have a range of the spectrum colours being produced on there. Okay, so we'll just put a prism there. That'll give us, now this is, the setup's not so much important, but we're to explain fully how these lines are formed. So these lines here, how they appear on the screen, are formed. Now, if you know what these are used for, is usually you would have, say, light from a distant star being directed, not through the gas, but directed onto the screen here of the spectroscope, or however the spectroscope does that. And the spectrum produced from that light from the star tells us about the composition of the star. Now in this case we've got white light coming through, we have the gas here, and the gas will absorb some of the frequencies of white light, and some of it will just pass straight through. Okay. Now the light that is absorbed will, if you think a single photon of that light that's absorbed hitting an electron, which is part of a nucleus, and exciting it, giving the energy to the electron to make it jump up energy levels. Okay, so the electron is then going to jump up an energy level to do that. And the first thing to note is when the white light, those frequencies do that, those frequencies no longer pass through. So you lose the frequencies that are used to excite the electrons. Okay, so my notation doesn't mean anything scientific, that's just a way for me to explain it. But then that electrons will eventually, or maybe instantaneously, but they will fall back down to their natural energy level, emitting some more photons, some radiation, electromagnetic radiation. The only problem is, when they emit that radiation, it's not going to be in the same line that it originally went in. It's going to be spreading out in all different directions in 3 dimensions, not just the 2 I've got here. So where that particular frequency of light cause those electrons to excite, and that frequency corresponds to the energy that the electrons gain when they jump up from E equals hf. Okay, the frequency of the light times Planck's constant gives you the energy. That's also the energy the electrons will jump up. It'll only absorb only absorb frequencies of light at the specific energy to jump it to an exact discrete level. That's kind of the whole point of this. Okay, so anyway, those frequencies are going to be darker on here because all this light is kind of being scattered as the electrons absorb that light wavelength of light, jump up, drop down, and it's converting it into photons going off all over the place. Okay, so that's why they'll appear darker. There's not as much light at that frequency striking the spectroscope or the screen.